Good morning, good afternoon, or good evening, depending upon where you live around the world. Here we have three options that was a development of the first one. So we started out with an idea here and developed it up as we went through, or we had ideas that would fit this example. One of the things I enjoy about making these videos is, and now don't take this the wrong way, I like listening to what I've said when I go to review the video. All of my videos are unedited, and as such I have to make sure that I'm saying what I think is correct, and if it's not, delete and I'll make it again. But in that process I get to hear the words coming out of my mouth being said back to me, and I go, oh, hang on, that's not quite right, or yeah, I didn't mean it that way. I wished I could do that in real life. But for this I made a comment about, let's just zoom in, do a wee bit of a hiding thing here, and I will hide that and switch on the X-ray. In that, I love that facility within SketchUp. Now, the ease of use of this particular design is that once your once your struts have been cut with the specific angle on their ends, we can then insert threaded rods, threaded rods, and they would be ideally in the center of the cut vertically, but they wouldn't then project into the neutral axis of the strut itself, which is a bit of a downside. And the fact that a single bolt like this would have to do a lot of work in high demand areas, which would be, in my design, there are a number of joints or hub areas that require a high demand. Anyway, I looked at this and I thought, no, that's good. Oh, what about nestling in or nesting into the hub, the end of the strut? Well, that's a good thing, because it helps to self-align the strut to the hub vertically, we'll say. So I went from there to this design where we actually, I'll hide everything there, bolt on a plate to the end of the struts. You make one style of this. This is just a rough idea, the first thought I had, where we use reasonably long screws, but longer would be better in this area here, such that we've got a good penetration. These ones happen to be 70 or 80 millimeters long, but I would probably go a little bit longer on these 4 screws. Now that meant that this plate, I'm suggesting maybe 10 mils thick. Why? Well, that's what the nut thickness would be if we were to use a nut. Well, if we had a 10 mil plate threaded well, we could then insert our bolts from the inside of the hub and thread into this plate. Now that means that a jig set up in your workshop, you could locate them specifically for the height. There might be a measurement requirement there is, and then because they're all identical, the hubs can be drilled with the holes identically spaced apart vertically, and then we'd have a very neat assembly. Now this one kind of caught me by surprise, and I thought, oh, I do like that actually, assuming of course we can get good penetration with these screws, because after all, this bolt here will be working overtime. And I think that in this scenario, the way I'm thinking, I would like a, let's say, some Loctite type of paste put in the hole before we put our bolt in, or put it on the bolt and wind it in, because they're so small, I'm going to leave that alone. I'm going to talk to an engineer before I make any bold statements, because I have a little bit of discomfort using short, stout bolts and being able to get enough torque. You may have to have I'll leave it alone. I'm way outside my wheelhouse. So we've got this nice, I think this is really, really nice assembly. Very neat. So the aesthetics of this are second to none. I'd rate this, now my preferred style is the Viking dome type star plates. I think that is a particularly elegant and versatile approach, but because I've got certain design criterion that the star plate won't meet, doing it in a fashion like this suits me better, or my design better. The one thing I'd have a little bit of concern with this is, does it scale? I think the answer is yes. And or how well does it scale? It will eventually come back to these screws, their ability to embed well and not pull out under extreme load. That I have a little issue with still, so I can't quantify it. Then I had a thought, what if, I'll hide these, what if instead of being at 90 degrees to the plate, they're parallel to the plate, the bolt insert. Now remembering this would have, which is not shown, a hole in the side of the strut through which a pipe would be inserted, and the threaded rod would go through said pipe, and there'd be a nut inside the pipe to thread into. That makes this a very strong, well able to resist high torque loads on the nut assembly. Now, one of the things that I made mention of as I started the video is that, or at least in another video, that the stability of this type of single fixing hub strut design means that high loads on the top could get some dislocation at this point. It's not inherently stable because it is in the center. Not wording that well. It is better if there is a dispersed fixing pattern, one where there is a fixing at the bottom and the top. Yes, you've doubled up on the number of fixings, but it is a fixing where it's spread over. It's like, in engineering terms, a double shear situation. If you haven't got double shear, this isn't, then you've got to make sure that everything is beefier and very good, or very well designed and constructed. Anyway, still like this. In most cases, the triangulation feature of a geodesic dome will have a very rigid, stable joint, one with much lesser fixing requirements. Understood. But because I have an open-sided dome approach, where we have 4 legs instead of the complete triangles and geometry going all the way down to the ground through multiple struts, the open design will place greater demand on this particular strut or joint. So whatever I do has to be a little bit over designed in some cases, especially seeing we don't have an engineer on board. Then this is where this was actually the reason for the video, believe it or not. After 10 minutes I posed a question to myself, and that's why I say you hear back your own statement. I said you've got to be careful about the benefit of doing highly accurate models. And one of the things is we can look at something on screen and go, yep, no problem. Go out to the workshop, yep, problem. Done. Because we didn't spatially think it through. And in this case, how do you, sorry about the big zoom, how do you tighten the bolts up or the nuts up? And in this case, I modelled a socket. This is my socket for my garage. It is accurate to the last ½ millimeter, there or thereabouts. But it shows that for me to get the socket onto the bolt, onto the nut, remembering it will be back this way, ½ an inch or 12 millimeters or so, with the actual drive mechanism on, I might not be able to get it in place. And this is not the tightest of design. This is just with the struts moved 60 degrees, so it was just a bit of a generic look at it. And also why you may start here, but you really do have to apply an example of this hub with the actual struts in place in their correct geometry. Anyway, I thought, well, we won't be using a socket easily in this scenario, but we could use open-ended spanners and ring spanners to take up the majority, if not all, of the tightening required on these nuts. And that was the point I was making as accurate a representation of the real thing as possible is probably a good idea, if not required. And I went back to how I assemble this. Do I use in this case it's a representation of a strip of the pipe itself bedded in. That is particularly neat. I made a representation of the plastic interface. This is a limiting factor on this design. If I wanted to torque up this nut, that really wants to be a solid piece of in this case plastic, that would resist any crush that would occur through torquing the 12 millimeter, in this case, bolt and nut. In all likelihood you could make it 10 mil. Wouldn't want to go any lower. I wouldn't want to go down to 8 mil, not for the size dome that I want to make. So 10 or 12 millimeter solid tube, solid rod with a hole drilled through it, cut at the required angle for this particular strut, washer on, and then the nut and torque it up. But open-ended spanners could get in here, of course, top or bottom, or a ring spanner, or you can even get the ratcheting ring spanner, but I don't know the wisdom of using that to exert lots of torque. You might find they don't last too well anyway. But I think that is a nice design. It has the ability, or flexibility rather, that it's easy to construct. Your neutral axis can be, jumped around there. The pipe that goes through the side of the strut that the threaded rod goes through can be placed anywhere along the central axis or neutral axis of the strut. Yay, double thumbs up for that point. In my preferred method, where we put the threaded rod in its square to the cut angle, the neutral axis varies on each strut dependent upon the angle of that strut. It varies quite a bit actually, but cosmetically we're going, that's the compromise, the variant point for the pipe that I'd tolerate, and the rest of it looks quite neat. Thank you very much. So it's a step forward if you were to consider using this method. I like it. I would consider using this for a pergola type scenario. One that's a little bit more open perhaps, not necessarily having a 100% water or weatherproof top, but some thought there. This one I like even more, mainly on the cosmetic side. The aesthetic side of this I think could be quite superior. It's elegant in its apparent simplicity, and if I can quantify the holding power of 4 screws in the end, I like this design. Again, I will question just how much loading it could take in comparison to the threaded rod going into or through a pipe with a nut on it, because we could probably quantify that, an engineer could quantify that a lot more precisely than the insertion of threads into the semi-end grain of a piece of timber. That's a variable. Don't know how you'd quantify it that easily, but as I mentioned, perhaps longer screws would mitigate that. You got more chance of it snapping at the point of the countersink. So in that, as I'm talking, let's just have a bit of a hide there. In that, it may be that rather than countersink, we have a pan head or wafer head type of screw. It would reduce the frailty of the head from snapping, because they will. You overload a screw, it will snap right at that point. No question. If it binds, it can snap anywhere along the shaft. But in this situation, the vulnerable point is that head, and if we can reduce the head issue, then we're on a winner again. That may require a slightly different recessing or countersinking of the head, because let's have a look. Oh, what have I done there? It's not that. Unguide, don't know what I've done there. And hide. Oh, I'll have to have a look at that. But the heads can't stick out too far, otherwise they'll bind with the hub. So what have I done? I better close this without saving. Very odd. Showing hidden content. Okay. There we go. I've got them set up for different keyboard shortcuts, so it's like, oops. Okay, anyway, we have to consider some of those points that I've just brought up. So, and with that, I'll end this and go outside and do something constructive outside. Rightio, we'll see you in the next video. Bye now.